हे देखो सोचो खोजो कुछ नया करके तो देखे, देखो सोचो खोजो कुछ नया खोज के देखे। एक्सप्लोरेशन, इन्वेंशन, इनोवेशन, मुक्तांगन एक्सप्लोरेटरी, मुक्तांगन एक्सप्लोरेटरी, मुक्तांगन एक्सप्लोरेटरी, मुक्तांगन एक्सप्लोरेटरी।
Good morning and a very warm welcome to all of you to the SciTalk series. Today we are to you with a new exciting topic on cosmology, astronomy and space science. It's a great pleasure to see so many of you connected online on a Sunday morning. I can see we have participations from all over India, from different states and villages. So let me quickly introduce you to Muktangan Explratory, who has brought to you this SciTalk series. As you can see on my screen, Muktangan Explratory was founded by Dr. late V.G. Bhide. I hope you all can see my screen. Yeah. So Muktangan Explratory was founded by Dr. late V.G. Bhide, the ex-Vice Chancellor of Pune University. With its two divisions, one in Kothur and the other in SB this is a unit of Bharatiya Vidya Bhavan, a globally recognized and a very unique science center. Explratory focuses on nurturing bright young minds. Here, students are promoted to observe, investigate, and through fun-filled activities, learn the scientific skills and principles. Every year, students participate in very large numbers. Over greater than 50,000 till now have benefited from its activities. They have developed a scientific mindset that allows them to innovate and invent technically in all walks of life. To know more, you do visit our Muktangan Explratory website, the Facebook handle, the Instagram handle, and the YouTube handles. If you have not registered yet, please do register on 7218-778851. Okay, to move on today with our new lecture series on cosmology, astronomy, and space sciences. Here you can see we have 6 different stories coming up. Continuing for you on this COVID times, we have different eminent scientists from NCRA, ICER, TIFR, ISRO, who are going to talk to you and make you marvel about recent happenings and trends in this field. Isn't it cool that you can just sit in the comfort of your home and listen to these 6 different stories along with your family and friends? At no cost, no travel, so let's discover wonderful things in this SciTalk virtual series. We are very fortunate to receive a foreword from Dr. Jayant Narayekar. So as you can see on my screen, Jayant Narayekar in his foreword mentions that these series on various aspects of astronomy will ignite young minds. Science is an unending exercise of searching. Experts will awaken students about this aspect with a point of view to search the unknown and get answers to your questions. With his best wishes, let's proceed to our first talk of this series. So, as you all know, our universe has neither been infinite nor it has been in existence for infinite time. It had a definite beginning some 13.77 billion years ago. It is not static and that it is expanding. Many scientists and cosmologists had reached this conclusion in the last century after understanding that most of the galaxies are moving away from each other. The history of this scientific quest is very interesting. It provides us a glimpse as to how research work in astronomy, astrophysics, spectroscopy has resulted in such a concept. The beginning of the universe is generally called the Big Bang. This is not a theory. This is a model. and a depiction of what could have happened at the beginning of universe. It's my pleasure to tell you that today, to tell you this story, we have with us Professor Pramod Kale. He is going to tell us the silent, unseen beginning. I'm sure you all must be wondering who is Professor Pramod Kale, and let me make a very quick introduction to him. Professor Pramod Kale is former Director Space Applications from Vikram Sarabhai Space Center, ISRO. Professor Pramod Kale joined the Indian Space Research Organization, ISRO, in 1962. His long and stellar career of 32 years is marked with various leadership positions. His very first position of a research student with none other than Dr. Vikram Sarabhai. Pramod Kale worked on satellite tracking at the Physical Research Laboratory, PRL Ahmedabad, and was a member of the first team to Goddard Space Flight Center, NASA, USA, for training in launching sounding rockets in 1963 and establishing the Thumba Equatorial Rocket Launching Station. Professor Pramod Kale went on to achieve several notable positions in ISRO and DOS. He was the director at the Vikram Sarabhai Space Center, Thiruvananthapuram, and Space Science Center, SAC. After retiring from ISRO, he was the executive director and the head of Microwave Antenna Division at Global Wireless Technology Limited, and also the director of the Global Information Technology Academy in Pune. He was the executive chairman of Muktangan Explratory. Currently, he is the president of Vasundhara Trust and Community Aid and Sponsorship Program. Professor Pramod Kale has been honored with many awards and recognitions, which include Aryabhatta Award of the Astronomical Society of India and Padma Shri in 1984. We are very honored to have you, Professor Pramod Kale. We request you to start with today's story. We are very eagerly waiting for it. Over to you. So before I pass on to Pramod Kale, a very quick announcement. Do keep yourselves on mute, stop your videos. Also, listen very carefully. I'm sure you must have a lot of questions. So do put them on the chat window and we will answer them at the end. Over to you, Professor.
Good morning, everyone. I'll be talking today about the beginning of the universe, and it's really a wonderful opportunity to talk about these subjects because this is the week, that is the World Space Week. Every year it is being commemorated to remember the launch of the first satellite, Sputnik 1, which happened in 1957 on the 4th October. During this week particularly, the theme given by the United Nations this time is how satellites are benefiting, or the satellite utilization is benefiting the mankind. When we talk about the satellites, it's good to know as to what was happening in the universe at some time and how it all started. Very early people had realized that everything in the universe is really in motion. Everything is restless. In the school, when we studied about Newton's laws of motion, one of the first law, I think, starts that if it is at rest, it will remain at rest. The question is, it is at rest with respect to what? With respect to a specific frame of reference. Because that itself, which is there on the earth, is moving along with the earth. The earth itself is going around the sun, and it is moving at a very, very high speed, 30 kilometers per second. The sun itself is also moving within the galaxy. The galaxy is moving within the universe. Everything is at in motion, it is at unrest. And the universe was not like what it today we see. It was something entirely different. It has been evolving. So let me start with this is about the universe. That is the silent, unseen beginning of the universe. It is generally referred to as Big Bang. I must say that I'm not an expert on the subject, the beginning of the universe. I'm going to share with you what I have understood from my study of this very fascinating subject. People from all the different cultures and civilizations have thought about this subject, wondered about this subject. In the last 120 years, our understanding of this subject has reached to the stage that it is today. Still, a very large number of questions remain unanswered. Subjects such as time travel, wormholes, black holes, dark energy, dark matter, multiple universes, parallel universes, and cyclic universes have attracted a large number of scientists, science fiction writers, and enthusiastic readers. As I kept on studying varying books, three books, namely The Birth and the Death of the Sun by George Gamow, Brief History of Time by Stephen Hawking, and The First 3 Minutes by Stephen Weinberg, were really eye-openers for me. Only after reading these books, I started seriously studying the subject, the beginning of the universe, or what everybody calls commonly as the Big Bang. Fred Hoyle had used the term Big Bang in a disdainful tone in a radio talk while comparing the steady-state theory proposed by him and the theory requiring a moment of creation propagated and supported by George Gamow. We must understand that the Big Bang is not a theory. It is a model or depiction of what could have happened at the beginning. It is a valid inference based on the evidence and not just a speculation. There is overwhelming evidence supporting this model. This year, during the various lockdowns caused by the COVID-19 pandemic, I got enough time to study various aspects of the Big Bang and refresh my knowledge. What is inside of a star? This is the first time I had heard about all these things in the lectures given by Professor Chandrasekhar in 1964. I was really very fortunate to attend the series of lectures, and he had delivered them on these lectures on the subject of radiative heat transfer in stars at the Physical Research Laboratory, Ahmedabad. At that time, I was given the responsibility of recording everything that Professor Chandrasekhar talked about, and that was really good fortune for me because it meant that in that our small auditorium, I always had the best of the seat available right in the front. I had understood for the first time something about astrophysics, as these lectures were about the extremely hot interiors of the stars. Our universe has neither been infinite nor it has been in existence for infinite time. It had a definite beginning some 13.77 billion years ago. It is not static and it is expanding. Many scientists and cosmologists had reached to this conclusion in the last century after understanding that most of the galaxies are moving away from each other. The history of this scientific quest is very interesting, and it provides us a glimpse as to how research work in astronomy, astrophysics, and spectroscopy has resulted in such a concept. The beginning of the universe is generally called the Big Bang. For thousands of years, the human beings have wondered, thought about, and speculated about the beginning of the universe. Even today, there are many questions about the beginning of the universe. The history of acquiring the knowledge about the beginning of the universe is very interesting. Astronomy, astrophysics, and spectroscopy in particular have provided us most of the answers to our questions. We normally associate a very loud, deafening sound or bang, as well as a blinding flash of light with any sudden explosion. Since the universe began with an explosion before even the birth of any star, there obviously was neither anybody to hear the sound associated with it, nor to see the blinding flash of intense light. Hence, I have titled this as the silent, unseen beginning. The space, matter, energy, and time all appeared together at the beginning of the universe. The implications of the idea that the time itself began at the beginning of the universe are far-reaching. Stephen Hawking has very extensively written on this particular subject, particularly about his ideas, his beliefs, as to whether the universe was created by God or not. Did it happen on its own? How did it happen? What are the implications when we say that the time itself began with the universe? And then we get various questions in our mind. Is the universe finite? Has it been always the way it is? When did it start? How did it start? Had God created the universe? If it had a beginning, will it also have an end? Is it cyclic in nature? Are there multiple or parallel universes? For any theory or the model of the beginning of the universe to be acceptable, it must provide some tangible evidence. It should also lead to the thought process that explains the present state of the universe. Basically, it is a description of the history. It should lead to the understanding of the abundance of the elements such as hydrogen, helium, lithium, carbon, etc. in the universe. Whatever the history, finally, it should lead to description of the universe as we observe it today. In the initial period, there was a concept that the universe was infinite, but then it resulted in a paradox. If the universe were infinite and had existed forever, we should be getting light from any direction. And this would result in the night sky being as bright as daytime. Every object would be heated up to very high temperature. This has been named, or this has been referred as Olbers's paradox. Olbers was a German astronomer. Since this is not so, the universe cannot be infinite and that it must have had a definite beginning. Stephen Hawking has given a proper explanation for this in his book, Brief Answers to the Big Questions. Although the universe seems to be much the same at each position in space, it is definitely changing in time. This was not realized until the early years of the last century. Up to then, it was thought that the universe was essentially constant in time. It might have existed for an infinite time, but that seemed to lead to absurd conclusions. If the stars had been radiating for an infinite time, they would have heated up the universe until it reached their own temperatures. Even at night, the whole sky would be as bright as the sun, because every line of sight would have ended either on a star or on a cloud of dust that had been heated up until it was as hot as the stars. So the observation that we all have made that the sky at night is dark is very important. It implies that the universe cannot have existed forever in the state which we see it today. Something must have happened in the past to make the stars turn on a finite time ago. Then the light from the very distant stars wouldn't have had time to reach to us yet. This would explain why the sky at night is not as bright as the day. In an infinite universe, we see a star in every direction that we look, and this means that every point in the sky will be bright, and whether it is day or night. We know that the sun radiates a very large amount of energy. When we calculate, we find that the sun radiates about 4 times 10 to the power 26 watts per second. That's a very, very large amount of energy, and it has been radiating this kind of an energy for a long time, and it will continue. Currently, the estimate of the life of the sun is that it will remain there for another 5 to 7 billion years. Eddington in the early years had suggested that fusion of hydrogen to form helium could be the source of the energy in the interior of the sun. Einstein's famous equation E is equal to mc squared gave the proper explanation for the source of the energy. In the core of the sun, hydrogen was getting fused and was becoming helium. Einstein was very famous for his playful ways, the way he initially started. Later on, he became very, very serious, but initially he was very playful. From the spectroscopic observations earlier, many astronomers had concluded that the sun had iron as the main element present. Now, whatever spectroscopic analysis that they had done, whatever they had been able to observe, it indicated the lines which were present in the spectrum corresponded to iron. Since 1880, when scientists had realized that the radioactivity could be the source of energy, the presence of iron could not account for the energy radiated by the sun, because iron is not involved in any of the nuclear reactions. In fact, iron could be the end product. Correct observations by Cecilia Payne indicated that not the iron, but hydrogen was the most abundant element in the sun. When she had started her own research work, and she started saying that whatever she is seeing in the spectroscopic results, this was hydrogen and not iron, many of the astronomers had completely put her down on that particular aspect. In some instances, she had to withdraw her statements, but then later on, other astronomers all over the world, when they started looking at what was happening, they realized that it was hydrogen, and therefore fusion of hydrogen to form helium could explain the source of energy in the sun. Not only the sun that we know, but also in most of the stars. When Newton had given his theory of gravitation, which indicates that all the objects attract each other, even he had realized that eventually the universe should collapse on itself. If everything is getting attracted, we have seen this thing happening with magnets and iron filings or any one of those experiments, that if there is only attraction, then it will finally collapse. When Einstein had given his theory of the space-time, he also had realized that the universe should collapse if only the attractive gravitational force were there. He had believed that the universe was static at that time. The collapse is certainly not happening, and some force which would not allow this to happen is required. And in Einstein's equations, he had postulated a cosmological constant. Later on, he realized that it was a wrong thing to do, and he called it as his gravest mistake later. These are the objects. They're all attracting each other. If they're all attracting each other, at some time, they will start coming closer and closer to each other. Whenever an object emits certain waves, maybe sound, maybe light, the observed wavelength by an observer changes proportional to the relative velocity between the object and the observer. The change in the wavelength is proportional to the original frequency or the wavelength and the relative velocity. Now, it is possible to determine the precise emission line or absorption line wavelength in a laboratory. We can actually calculate also considering the atomic theory which we know today. Thus, if the object were to move towards the observer, the spectrum would be blue shifted. And if the object were to move away from the observer, the spectrum should be red shifted. It is possible to detect such a shift using instruments. We see the stars and they don't appear either blue or red. That is because they're not moving at extremely high velocity. In order for the star to appear either red or blue, it would have to move at a very, very high speed. So this is the Doppler effect. As the object is approaching us, which is emitting a sound, maybe a car with a horn or maybe a railway engine, its sound gets louder because it is coming nearer, but also its frequency changes. And as it moves away, the sound gets feebler and its frequency reduces. In the diagram here, we are seeing that the same object, when it is emitting a sound or light, in this case light, as it is approaching towards one of the observers, it is blue shifted. As it is receding away from one of the observers, it is red shifted. And the same thing is actually shown in the spectrum diagram also, where the lines you can see, they are shifted from one to another. The same line which is observed in the laboratory is shifted towards blue when it is moving towards you, and it is shifted towards red when it is moving away from you. Let us look at what does it really mean. If a spectral line of hydrogen, normally at 500 nanometer or 0.5 micron, as observed in a laboratory on the Earth, is observed in the spectrum of a star to be at 500.1 nanometer. That 0.1 nanometer change that occurred is due to the relative velocity. So we can calculate how fast the star is moving toward or away from the Earth. As the light is shifted to a longer wavelength, the star should be then moving away from us. From 500, it has become 500.1. We know that the speed of the light is 300,000 kilometers or 3 into 10 to the power 8 meters per second. Lambda is the wavelength observed in the laboratory, and delta lambda is the change in wavelength observed in the star. And then, as what we see is 500 minus 500.1, it is minus 0.1. The velocity of the object is given by the expression V is equal to C into delta lambda divided by lambda. And this turns out to be minus 60,000 meters or minus 60 kilometers per second. So this star then is moving away from us since the velocity is minus. Very careful observations of the faint clouds or nebulae seen by smaller telescopes had indicated that these could be galaxies. Very early, the measurements which were being taken were taken by telescopes with small mirrors, something of the order of maybe 20 to 30 inches or so. When larger and larger telescopes started coming up, people started realizing that what we were seeing as faint clouds or nebula were actually galaxies by themselves. With larger telescopes, these observations were confirmed that these were galaxies. Now, spectroscopic observations had indicated that some galaxies were showing blue shifts and larger number of galaxies were showing red shift. Astronomer Edwin Hubble had concluded that most of the galaxies were receding away from the Earth. Now, this was a very, very important observation, and that is, it would mean that the universe was expanding. It would also mean that it was not static. What Edwin Hubble found was that the recessional velocity, that is moving away from the object like Earth from where we are observing, and distance to the galaxy. The distance to the galaxy was measured by considering various different stars in those galaxies, and the recessional velocity was calculated on the basis of the spectral shift, blue shift or red shift. And when he plotted all these observations, they would formed a simple linear relationship, and that would really mean that they were moving away. And this is the one that gave rise to the Hubble's law, or as well as the Hubble's constant. In the initial period, based upon the observation which was there, and that was the Doppler shift as observed in the spectrum. But the distances to the galaxies were determined using very simple measurements. And in the initial period, whatever he had indicated, Hubble had indicated, turned out to be not really correct. Because from this particular concept, which I'll be explaining later, certain different ideas people started coming out with. It was seen that farther away the galaxies were there, they were moving away at a faster speed. This resulted in the formulation of the Hubble's law. Now, this law is now known as Hubble-Lemaître law. In the initial period, there were certain errors, and these were corrected later. Because of these particular errors, Einstein was not convinced earlier about the expanding universe, but later was convinced. What was happening was that from the Hubble's law, when people were able to calculate the beginning of the universe, so when universe could have started, those numbers looked rather absurd because they were getting answers indicating that the universe was younger than the Earth itself. Because the age of the Earth was possible to be determined with a much better accuracy due to the geological knowledge what people had, as well as by the radioactivity as seen. Currently, the accepted value of the Hubble constant is 72 kilometers per second per megaparsec. Now, megaparsec is a measure of the distance, and it is equal to 3.09 into 10 to the power 19 kilometers. Since the galaxies were moving away from each other, and as their speeds were related to the distances from the Earth, it is possible to carry out a straightforward computation which indicates that in the past, these galaxies were closer to each other. This is a very interesting concept that today when we say that they are moving away, so at some time they would have really been together. The inverse of, or the reciprocal of the Hubble constant gives the time when the galaxies were at their closest to each other. And this also allows us to determine the age of the universe or the time when it actually began. Let's hear a video that somebody is moving forward or coming back. So one can go forward once we know that speed, we can project it back and set it from where it was originated. Here is something which fallen down. That was the video, but you can play it backwards. Today we are very familiar with this thing we see in the replay. We can see all kinds of things on the cricket matches. There is a fantastic video of a rocket taking off. There is another one of a rocket coming back to land. So we can move forward or backward. In these particular images, the same thing we can also think about in the universe. And from the Hubble constant, the age of the universe can be calculated. If we take the inverse of the reciprocal of the Hubble constant, h naught, then it turns out, since it is speed is there kilometers per second and per megaparsec. So we can calculate this as 13.6 billion years. Now you can see here that a small mistake in the distance measurement can lead to a very different number as far as the age itself is concerned, age of the universe is concerned. LBERS, he was a, I think, Catholic priest. He had, for the first time, differed with respect to the church and said that, okay, universe began much earlier and it started with one single explosion and it was continuously expanding. Now, this completely was in contravention of what the Bible says, what the Old Testament says, what the church indicated, but he stuck to his points, and then later on it was proven that what he was saying was correct. And he had derived that it was expanding from the equations of the general theory of relativity. So in the initial period, even Einstein was not convinced that LBERS was correct, but later on he agreed that yes, LBERS was correct. In the PhD dissertation, Ralph Alpher had argued that in the Big Bang, hydrogen, helium, and other heavier elements would be created, and it would happen in the correct proportion of their abundance in the early universe. The original theory had neglected a number of processes important to the formation of heavy elements. Later developments indicated that the hypothesis of Big Bang nucleosynthesis was consistent with the observed abundances. Formally titled The Origin of Chemical Elements, it was published in April 1948 issue of the Physical Review. The important thing here to remember is that as the universe began, immediately some of the elements were formed, and hydrogen is the lightest of the element, basically one proton and one electron. Helium has got 2 protons. So these were the earliest of the elements which could be created. But any theory that we think about has to be consistent, so that it could actually get to the point that it can indicate to us that even extremely heavy elements like uranium could be created within the universe. Fred Hoyle gave the correct theory regarding nucleosynthesis of the heavier elements observed in the universe. Now, stellar nucleosynthesis is the creation of chemical elements from fusion reactions within stars. Stellar nuclear synthesis has occurred since the original creation of hydrogen, helium, and lithium during the Big Bang. As a predictive theory, it yields accurate estimates of the observed abundances of the elements, and it explains why the observed abundances of elements change over time, why some elements and their isotopes are much more abundant than others. What was necessary was that how 3 nuclei of helium could join together to form carbon, and that was the important theory given by Fred Hoyle. Fred Hoyle had also given his steady state theory for the universe. The cosmological theory, as developed by Bondi, Gould, and Hoyle, is known as the steady state theory. As per this theory, the average properties of the universe never change with time. New matter must be continuously created to keep the density constant as the universe expands. But this model was largely discredited later. As per this model of the universe, when the universe expands, new matter is created in the growing gaps between galaxies. The universe would thus maintain a similar density at all times and would last for eternity. So the creation of the new matter was not possible to be really proven, and this was the stumbling block at that time. That's Fred Hoyle, and along with Fred Hoyle, Jayant Narlikar also worked on this particular theory for some time, but basically he worked later on Hoyle's work regarding gravitation. Steven Weinberg has described the beginning of the universe, or the Big Bang, in a very, very simple fashion. So let me quote from there. In the beginning, there was an explosion, not an explosion like those familiar on Earth, starting from a definite center and spreading out to engulf more and more of the circumambient air, but an explosion which occurred simultaneously everywhere, filling all space from the beginning, with every particle of matter rushing apart from every other particle. All space in this context may mean either all of an infinite universe or all of a finite universe which curves back on itself like the surface of a sphere. Neither possibility is easy to comprehend, but this will not get in our way. It matters hardly at all in the early universe whether space is finite or infinite. At about 1/100th of a second, the earliest time about which we can speak with any confidence, the temperature of the universe was about 100,000 million or 10 to the power 11 degrees centigrade. Now, this is a much hotter than the center of even the hottest of the star, so hot, in fact, that none of the components of ordinary matter, molecules or atoms, or even the nuclei of atoms would have held together. They would have disintegrated at that particular temperature. In the beginning, electrons, positrons, neutrinos of various kinds and photons were produced. As the space expanded, it cooled down and other fundamental particles started appearing. These particles were created from pure energy. These particles, electrons, positrons, and neutrinos, photons, were continuously being created out of pure energy and then, after short lives, were being annihilated again. Their number, therefore, was not preordained, but fixed instead by a balance between processes of creation and annihilation. From this balance, we can infer that the density of this cosmic soup at a temperature of 100,000 million degrees centigrade was about 4,000 million times or 4 billion times that of water. Steven Weinberg later on got Nobel Prize for his work. In 1948, Ralph Alpher and Robert Herman had predicted that there should be cosmic background radiation. This was actually measured and proven to be so by Penzias and Wilson. The observed radiation had the spectral properties of thermal radiation. These measurements resulted in full support to the theories of the Big Bang and expanding universe. The theory regarding the static universe could not explain this thermal radiation background. Alpha, Bethe, and Gamma, it's a very famous paper called as Alpha, Beta, Gamma, had predicted that as the universe expanded with time, the wavelength of the primordial light would have also been stretched, as space itself has been stretched. This concept, I will talk about it later again. The light then had a wavelength of roughly 1,000th of a millimeter or 1 micron, where it originally emerged when the universe was about 300,000 years old. According to the Big Bang model, the universe has expanded by roughly a factor of 1,000, and therefore the light should now have a wavelength of a millimeter. Penzias and Wilson, they were working with AT&T, and this antenna that you see in the background is a big farm which was used for communicating with satellites. And they wanted to make certain that the antennas were actually showing least amount of noise picked up from the universe or the galaxy, and particularly the center of our galaxy. They were able to improve the antenna up to a point. Beyond that, it was not possible to be improved. And later on, while working on this entire aspect, they came to the conclusion that what they were getting was actually the background radiation which was coming from the universe. Everywhere, in any direction that you look, you will always get this particular background. 1964, this thing happened. And I remember that for us working in the beginning of the satellite communications, this was a major thing because an antenna developed for the satellite communications had resulted in this kind of discovery. from those times onwards, we had two radio astronomers that I know who were working with us in India. One was Professor Bhosley. He passed away earlier, and just last month, Dr. Govind Swarup also passed away. Alan Guth has later on come up with a totally different kind of an idea, and that is, in the initial period, suddenly there must have been an inflation. Now, while it is not expanding at a particular rate now, but that couldn't have been the rate in the beginning. In the beginning, something much faster should be happening. And as per this model, in a very short time, the universe inflated. It was doubling in every 10 to the power minus 37 seconds and continued to do so till 10 to the power minus 35 seconds. But during this time, there were more than 100 doublings. This would then explain also as to when we observe the redshift, it indicates sometimes the velocities which are very, very high, 60,000 kilometers per second. So that's a very, very high speed. And instead of the item being actually moved away at that high speed, if the space itself were stretching. So this was the very specific idea that Alan Guth had given. Now I can see it here. Let's say that there are quite a large number of dots on a balloon. As we expand the balloon by blowing it up, you can see that every dot is moving away from each other. So either they were moving, but between the galaxies, yes, the distance has increased. So the space itself would have stretched. Same is the case here. We have got two axes, X and Y, and the third axis is time. So in time, it is continuously expanding. This is generally depicted as the general timeline for the universe. It started directly from the universe. In the initial period, it went through the inflation. We could see that in the initial period, the density of the universe was so high that the light from that particular time couldn't come out. And those are the ones which are called as dark ages. And then came the development of the galaxies, the planets, etc. And the first stars started appearing because it took that much time for all these particles to come together as clumps and form a star. And that took about 400 million years or so. This is the timeline for the kind of discoveries that have happened and kind of things that have happened earlier. The 1054 AD, that was the Crab supernova which appeared, has been observed and reported in Chinese literature also. It has been reported in some of the Indian literatures also. 1609, Galileo built first telescope. 1665, Newton describes gravity. 1905, Einstein publishes relativity. 1929, Hubble discovers universe expansion. Quasars were discovered in 1960. Microwave radiation discovered in 1964. 1967, pulsars were discovered by Anthony Hewish and Jocelyn Bell. Supernova 1987, which occurred. 1990, Hubble telescope was launched, which gave us extremely large amount of information. And in 1990 itself, the Cosmic Background Explorer, COBE, actually started giving us quite a large amount of information. COBE, YMAP, each one of these gave us the large amount of information. And Hubble telescope in the 1993 was repaired and continued to function for a very, very long time afterwards. The Stephen Hawking had actually explained some of the things in his own way. That is, he said, the creation of the universe requires mass, energy, and space. The famous equation E is equal to mc squared simply means that mass can be thought of as a kind of energy and vice versa. So instead of three ingredients, we can now say that the universe has just two, energy and space. So where did all the energy and space come from? The answer was found after decades of work by scientists. Space and energy were spontaneously invented in an event we now call as Big Bang. At the moment of Big Bang, an entire universe came into existence, and with it, the space. It all inflated just like a balloon being blown up. So where did all this energy and space come from? How does an entire universe full of energy, the awesome vastness of space and everything in it simply appear out of nothing? The great mystery at the heart of the Big Bang is to explain how an entire fantastically enormous universe of space and energy can materialize out of nothing. The secret lies in one of the strangest facts of our cosmos. The laws of physics demand the existence of something called negative energy. When the Big Bang produced a massive amount of positive energy, it simultaneously produced the same amount of negative energy. In this way, the positive and the negative add up to zero always, and it is another law of nature. So where is all the negative energy today? It is in the third ingredient in our cosmic cookbook, it is in the space. This may sound odd, but according to the laws of nature concerning gravity and motion, laws that are among the oldest in science, space itself is a vast store of negative energy, enough to ensure that everything adds up to zero. Hawking has given a wonderful explanation how the universe began from zero. According to him, from the zero, positive energy as well as negative energy were created. The positive energy had resulted in all the fundamental particles which we find in the universe. The space is the manifestation of the negative energy. We know that when we consider the attractive gravitational force between two objects, it decreases as per the inverse square law. And the gravitational potential energy is always then considered as negative. When we observe the universe through large telescopes, through satellites, what we see is that the observable gas clouds, dust clouds, stars and galaxies in the universe indicates that something is missing. Both the mass and energy in large amounts are missing. Since this mass does not interact with electromagnetic waves, we cannot see it, we cannot detect it, and this matter is generally called as dark matter, and the missing energy required to account for the gravitational effects is called dark energy. Cyclic universe is a concept that is being explored for a long time. Just as the universe now is in the expansion mode, it could stop expanding and then start contracting. It could then collapse on itself and end up in a singularity. After that, it could begin again. We have this kind of a concept in our Indian literature, and it is being looked at by many people. But yes, okay, such a thing as a cyclic thing could be happening. Let me conclude by quoting from Stephen Hawking. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. These are the references which I have used: The Birth and Death of the Sun, George Gamow; Brief Answers to Big Questions by Stephen Hawking. I think this was considered as his last book before he died. Brief History of Time, Black Holes and the Baby Universes, and The First 3 Minutes. The biography of the world's most famous equation, David Bodanis, Big Bang by Simon Singh, and The Inflationary Universe by Alan Guth and Paul Steinhardt. Thank you.
Thank you, Professor. It was great to have so much of knowledge from you. We have a lot of questions from various students and participants. Let's start with questions. So the first questions come from Sharmila Joshi. Do the laws of physics work in black holes? Hello, can you hear me, sir?
I can hear you. I'm not getting the question.
So what are those, to expand it further, what are those laws of physics that would work in black holes? How do they
The,
apply?
the laws of physics remain exactly the same as what we know. The only problem in trying to apply such laws in black hole, the problem that happens is that the time comes to a standstill inside of a black hole, and therefore, how to apply these laws becomes a problem.
Yeah, thank you so much, sir. The next question comes from Mandar Sathe. Can the Doppler effect be used to detect asteroids or comets coming towards the Earth?
Uh, it is definitely possible to think in that particular direction if we were to actually get reflections from these comets or asteroids using radars, then it is possible. By itself, they are not really moving at such a high speed that we could detect their speed using the Doppler effect. People have tried such things in spectroscopy, but I have not seen any specific report indicating that they are successful.
Thank you. From Shreyas Patankar, is there any estimate of how many solar systems would exist in the universe? Can we find that out?
Okay. What has been expected is that there are about 1.5 trillion suns equivalent stars in a galaxy. And such 1.5 trillion galaxies are there in the universe now. How many of the stars can have solar systems? When we talk about solar system, what do we mean? We're looking at a planet or some of the items which are orbiting around a star. There are a large number of solar planetary systems which are called generally as exoplanets have been discovered, and we will be able to discover more and more such systems. And I don't think that there is any point in estimating such numbers because these are going to be extremely large. We are always looking at planetary kind of a system because at a planetary system, what happens is that if we are at a, if there is a star like the sun, and if the planet is somewhere at a distance of about 150 million kilometers away from it, then it could have temperatures like that is what we have on the Earth, and maybe then life could exist. That's why everybody is looking for as to whether there are planetary systems or the solar systems as they are called. But we have yet to find any such system which life on it.
Thank you so much, sir. We have a lot of questions pouring in, but we'll stop here. They can get in touch with you later, maybe. So, yeah, so thank you so much, sir, for spending your valuable time with us and giving us so much wonderful insights on Big Bang. We understood different kinds of elements that are abundant in the universe and how different theories, Doppler effect, are actually supporting the expanding universe. It was so interesting to know that we can actually calculate the age of universe and find out how galaxies are expanding. The cosmic microwave, background radiation, the inflation theory, the Einstein's equation helping us to understand the creation of universe. It was so wonderful to hear and of such amazing theories. We thank you so much for spending your valuable time and giving us so much knowledge here.
Thank you.
Thank you, sir. With this exciting talk, I'm sure all of you are eager for the next. So the next lecture will be our universe introduction with the speaker, Mr. Parag Mahajani. So do not miss this opportunity. Before we drop off for the day, let me tell you we had a record participation from all over India. We would like you to spread other word and join in the next session along with your family and friends and register to the series. Also, as soon as the corona conditions restore, we invite you to Muktangan Exploratory and take the exploratory, immerse activities and immerse in them at the center, of course, taking care of your safeties. We will share with you the feedback form and you can let us know how you find these lecture series. Do tweet for the feedback as well with the hashtag SciTalk and hashtag Muktangan Exploratory. Take care, be inspired, stay curious. Do let me turn next Sunday.